Seasonic recently updated its popular Focus GX line, making it compatible with the ATX version 3.1 and PCI Express 5.1 standards. The line consists of 3 models with capacities ranging from 750 to 1000 watt. All have compact dimensions with 140mm depth. Despite the small dimensions, Seasonic fit 135mm diameter fan to keep noise output low. Seasonic also talks about the OptiSync design, which brings a new PCB layout to the Focus version 4 units, aiming to increase reliability by improving heat dissipation and airflow. According to Seasonic's claims, the new PCB design offers an 8-fold increase in heat dissipation, keeping the operating temperatures low and increasing the PSU's reliability. The PSU's small dimensions and the unique design of the fan grille make an appealing combination. On the PSU's front side, you will find the AC receptacle, the power switch and another switch to toggle on/off the fan's semi-passive operation. Around the back, the modular panel has 11 sockets, including a native 12V 2x6 one. There are enough cables and connectors to handle the PSU's maximum power without any issues, including 2 EPS, 3 PCI Express 6+2 pins on dedicated cables and a single 12V 2x6 cable with a PSU's setting for 600W. According to Intel's test plan, it should be at 450W, but most manufacturers go to full power on this cable. The EPS and PCI Express connectors mostly use 16 AWG gauges for lower voltage drops. The number of peripheral connectors is sufficient and the distance between the SATA connectors is adequate. On the contrary, the 4-pin Molex connectors are relatively close to each other. Despite the small PCB, plenty of space is available and the distance between parts is large to allow for enhanced airflow. The large vertical PCBs on the sides allow for an uncrowded PCB. One holds the ePFC converter and the main FETs, while the other daughterboard holds both DC-DC converters that generate the minor rails. Seasonic used surface mounting FETs and tiny heatsinks since the PCB also cools them. This is an interesting design to have a vertical board holding a significant part of the PSU's primary side. Speaking of the primary side, a full bridge topology is used for enhanced reliability and increased efficiency. On the secondary side, the 12V FETs are installed on the top PCB side, so they come in direct contact with the fan's airflow. Overall, the soldering quality is good and all parts that Seasonic used are of high quality, including Nichicon, Rubicon, Chemicon and FP Cap capacitors, along with Alpha and Omega and Xperia FETs. Moreover, the cooling fan is by Honghua, Seasonic's favorite fan manufacturer. It is always nice to see new PSU design since technology in this IT sector doesn't move as fast as in other sectors, for example CPUs and GPUs. That said, I would like to see the MCU handling more parts and not only playing the role of the fan controller. Nonetheless, having a digital fan controller is great since its programming is easy and provides more options than analog fan controllers. Still, you have to program it correctly, and creating a good fan profile is easier said than done. The 12V OCP triggering point is higher than 130% at cold conditions, but drops notably at high temperatures. The minor rails also have notably lower OCP triggering points at high temperatures, but in general, the triggering points are set high, especially on the 3.3V rail. The same is the case for 5SB, where OCP exceeds 200%. The overpower protection is set pretty high at low temperatures, but drops significantly at high temperatures to protect the PSU effectively. All other primary protection features are present, but fan failure protection should be implemented, especially since an MCU controls the fan. Load regulation is tight only at 5V. The 12V rail's load regulation exceeds 1.5% because its voltage level is too low at the 20W load, which is my start point at 11.893V. At 40W load, the 12V rail climbs to 12.074V. If I took the 40W load test as a reference, the load regulation at 12V would be 0.38%, which is pretty tight. Ripple suppression is good. The transient response is satisfactory at 12V and pretty good at 5V, but needs to get tighter at 3.3V. The PSU passes all ATX version 3.1 transient response tests, but the 12V drops low. The 12V rail doesn't perform well, dropping low on all tests. Efficiency is not that high on all load ranges, still the PSU surpasses the 70% threshold with a 2% load. The average efficiency is notably lower than the previous GX1000 model at 115V, while the difference gets smaller at 230V. The ePFC converter needs tuning for higher power factor readings. The 5SB rail should be more efficient at 230V. Vampire power should be lower at 230V. The PSU's average noise output is close to 28 dB at both voltage inputs, so it is low enough but not as low as other offerings in this wattage category. The semi-passive operation is between 60 and 85 W on the minor rails with a load on the 12V rail up to 350 W. Apparently, the programming of the MCU that controls the fan speed goes wild with the load pattern that I used in this test, but this shouldn't be the case. I like that I can get the worst case scenario through this test and not the ideal one, because in real life a PSU will be treated with a wide variety of load patterns, depending on each user's system and utilization. Moreover, users need to understand that most fan speed profiles also indirectly consider the load applied to the minor rails through the appropriate thermal sensors, because the respective DC-DC converters lag the appropriate heatsinks, so they rely on active cooling to lower their operating temperatures. The DC-DC converters, as their name implies, receive DC input and not AC, so the AC input voltage doesn't affect their efficiency and thermal loads. This is why, when you push them to the maximum, the fan speed will be regulated at the same levels whether you have 115V or 230V input, and this is why in many modern PSUs the 115V and 230V fan noise speed and fan speed maps are identical. There can be major differences only when other parts of the PSU, except the DC-DC converters, get way hotter at 115V compared to 230V input. These parts are typically up to the ePFC converter, where the input voltage is boosted at around 385V DC at the ePFC converter's output. The 230V fan noise profile is similar to the 115V one. The PSU's overall performance is not competitive. The new Seasonic Focus version 4 line uses an interesting PCB design, allowing for lots of room between components, so airflow can be high without pushing the fan speed. Nevertheless, the PSU's average noise output is not among the lowest in this wattage category. The same goes for its average efficiency and overall performance. It seems that the new design didn't help in improving the overall performance, with the previous GX1000 model scoring a bit higher than the new model. The low starting voltage level of the 12V rail affecting its load regulation, the average power factor readings, the sky-high inrush currents, the increased vampire power at 230V, and the high voltage drops at 12V in the ATX version 3.1 transient response test are the main culprits behind the unit's low overall performance. At least ripple suppression is good. Overall, I believe that Seasonic should push for higher performance given the price tags of the new Focus version 4 units, which are pretty high. The GX1000 V4 has an MSRP of $190, while the NZXT C1000 and the Montec Titan Gold are listed for $150, offering higher overall performance. The NZXT C1000 is also less noisy, with an average noise output below 25 dB. Moreover, I noticed a strange fan operation in the CL test, where I applied close to 1500 different load combinations, with the fan starting spinning from zero load with over 800 RPM and noise output exceeding 25 decibels. As I noted in our Discord channel, I can fully monitor and log the results of my test and analyze the corresponding data. Still, I cannot know why a PSU's fan speed profile behaves like that because I don't have access to the code that drives its fan controller. I am the test engineer and not the guy who designed the hardware to know why it behaves like that. My job as a test engineer is to find the worst possible scenario and all the issues a user could face. Before investing in a new power supply, read my best ATX version 3.x PSU's article on hwbusters.com to check all alternative PSU offerings. You will also find the product's review on the same site. That's all. Bye bye.